what we did last time. So finding the largest possible enclosure, rectangle enclosure with a given perimeter. That is how you want to express it geometrically. The perimeter, 100 yards, is given, and then you find the largest area. Okay, on that, as we did it, we had encountered relations over there. Width plus depth is equal to 50. We extracted functions from it. W is equal to 50 minus d. Okay, it was very helpful for us because we were then able to express our function that our area, okay, as also a function. Okay, so here's another. This is another function, also function. Okay, and that solves the problem because then it becomes into this simple machine producing outputs from inputs. So inputs are, as you can see here, the d, the depth, and the outputs are areas, and then you pretty much you have your function in your hand because you can either get as much data as you like, and we did. Okay, or you can plot it. That is very revealing frequently, and that's what we saw, and then the problem was solved. Okay, so that is the direction we are pursuing. More and more functions, and the variety of problems of this kind are enormous. And even if you have only a couple of variables. So you can modify this problem, for example, and ask yourself what happens if the shape of the enclosure might be different. Maybe it's circular or something like that. Or another simple problem with virtually no difference in the way you carried out the computation is the idea when the enclosure is built adjacent to a river. So that way you save on fencing material because you don't need to fence on the side of the river, and so you have only three sides like this, and then so width dd, and then so everything changes right away, but the plan is still the same. You still have a relation, right? Relation d plus w is equal to 100. Okay, that's your relation. You can extract a function from it. You can plug it into the formula for the area, which remains the same, and then you plot it, and you have pretty much the same, virtually no difference in the answer. Maybe let's take a minute and do that very quickly. If we modify the problem, I don't want you to think that this is everything we have done applies to this particular situation very specifically. But like I said, the enclosure is built adjacent to the river. Okay, so this is the river. Okay, so there are only three sides. Then let's quickly modify this. So this is the solution to our problem for the we started with. Stupid. Doing it again. Oh, come on. Okay, so let's modify. What do I need to modify in order to get the new situation? So the area is still the product of the depth and the width. What about the relation? How do we express the width in terms of the depth based on this? What's the relation between depth and width in this new situation? I think so. Yeah, well, let me just write it out. So it is 2d plus w is equal to 100, right? And then, so it means that my width will be 100 minus 2d, right? Okay, so once again, a relation that comes from, in other words, it uses restriction, constraint, in other words. So constraint on the w and d takes the form of this equation, and then we treat it as a relation. But really, if we want to solve the problem, we express it as a function. So w is expressed in terms of d, and so all we have to do is just to put d in there. Okay, so 100 minus 2d will be put in this column over there. 100 minus 2d over here. Okay, so let me change the formula here. 100 minus 100 minus 2 times this little thing. Okay. Okay, so the graph looks about hold on, why does it look exactly the same? What?
The numbers, the x and y axis changed.
So it seems that nothing has changed except for the height, right? Because it's still a range between 0 and 50. So what has changed? So it turns out the answer is the same. The width should be, the depth should be, it appears to be still 25, right? So, but it is a very different if we look back at the picture. So if we are talking about four-sided rectangle, the best one was a square, and here it's not. It's not. It is stretched, as a matter of fact. It is 2 times 1, like this. Oops. This is the answer. So the width is twice the depth. So it is actually better to stretch your enclosure along the river in order to save on the to produce the largest possible area. Okay. So, but the plan is the same, and that is the main thing here. What to do about word problems, but also illustration of this has been an illustration of how functions emerge and allows us to solve problems. Okay, so now the second source of functions. So more functions. Is very goes way back. It's motion. So this time we're not going to worry about relations anymore because if you want to talk about motion, the functions are there very explicitly. It is what is motion if not location, as it depends on time. Okay, so the motion that may have happened already, you're planning that motion for the future, but the idea is you know time, you know location. That's the dependence. Okay, so you time say x, location y, okay, and then you have your function f, y is equal to f of x. So there is no ambiguity about it. If you cannot be at two places at the same time, so it's not a relation as a it is a relation obviously, but it is a kind of relation that is also a function. So we will just concentrate entirely on functions. So once again, I don't know. Let's say 0, 1, 2, 3, 4. That's time in one column, and then you have location. Say 0, 1, 2, 3, 4. Okay, at this point, so this is an example of time, location. You know time, you know location. The dependence is like this, direct. You have to be more specific if you want to go on and study something more complicated. here, and that is you have to point out the exact relation, and you start with function starts with the domain and codomain. So domain, this is the domain, and it has to be pointed out, codomain, also known as inputs and outputs. Okay, so you have to specify them. So, so specify before you start thinking about the relation between them, the function, which is the relation. So for example, if you want to be specific, you can say time x every minute for 10 minutes. So in other words, it will be simply numbers from 0 to 10. Okay, so that could be your x. Time moment, so not time intervals, but time moments. So at every moment of time, you whether something has happened in between, we don't care. We just say at every moment of time on the strike of your clock, you ascertain where you are, and that will be the function. But at this time, you just know whether it is this time or not that time, and so you specified what moments of time you will be concerned about. Now, space or location, y, maybe every milestone. So let's say we're driving. So we're driving on the road. This is my car. Okay, and then we just detect milestones. Maybe for 10 miles. Okay, so coincidentally, it might look exactly the same as for time. We just keep in mind that we keep these two separate. Okay, so so far these are two separate. You pointed out what they are, but then once you get to talk about your function, you have to say, you have to express that relation, and it has to be very specific. What makes a motion specific? It's like a little story that you may have driven around, and so you know what has happened. And if you describe it specifically, you'll know how it looks. So, for example, what? So I drove for 10 minutes, and at speed 1 mile per minute. Okay, so that would be an example of a specific function, and which is pretty much what I have started to do on the right. So at time 0, you at location. Well, this is I did not specify one part in the beginning to make it specific because it depends on where I was initially. So starting at 0. So you're starting like your initial location is at 0, and then you drive for 10 minutes at speed 1 mile per hour, which means that after 1 minute you will be at 1 at the first milestone, and then the second after 2 minutes, and so on, and then so that will be your function up to 10 and 10. Okay, so that ends it. That is your whole function. Okay. More generally, like I said, as long as you can describe specifically what has happened, you will have you will have a function, but you don't have to describe it with words, as I did over there. You can just describe them with data, which is I have on the left. So any kind of arrangement of numbers, well, almost any, will correspond to motion. So so describe with data. So a table could be, once again, well, let's start to so x, y. Okay, so the first column is always the same. and the second one is not necessarily. So I could throw any data. So suppose once again, so how about I start with 1, 1, 1, 2, 2, no, 3, 4, 5, 5, 5, 5, 5. Okay. I threw any numbers pretty much arbitrarily in the second column. The first column is given. Remember that we even call it the independent variable, and the inputs are determined ahead of time. And all functions, all of these functions will have the same domain. Okay. The codomain is also the same. It has been specified, but the relation might be different. So I threw such just some numbers. And at this point, I could go backwards from verbal description to numbers, as we did last time. I can now go from data or numbers, which I have, to a verbal description. So what do you see here? So this is where you find yourself, at what milestone you find yourself after every minute of time. Every minute of time you look at yourself, and you not yourself, but rather look at where you are, and that's what you discover. So what has happened?
The speed you're moving is different?
Yes, okay. It is a description. It is a description, as I asked, but ideally I would like a description that would be complete, so that we can actually go backwards and recover that information from the description. So as specific as you can.
Certain milestones.
That's right. So that would be a good start to start describing, to say start at 1, the first milestone, not the first, but milestone with 1 on it. Okay. And then what happened then?
Didn't move.
Didn't move, right. Hypothetically, you may have driven, but then you ended up, after a minute, you ended up backwards, so we don't know. It doesn't matter. That is not part of our investigation. So you didn't move for a while, in fact, for like 2 whole minutes, and then what?
Milestone 2.
Yeah. Okay. Yeah. Move to 2, then 3 and 4, and then 5, and then what? Stop again. Stop. Okay. You can say, in fact, if you want to describe this in a kind of a more profound way, in a way that might be revealing for the future, you are moving 1 mile at a minute. Right, so for the future, that would be an important way to describe motion, if you can say how fast you're moving. Okay, so as we have done this before, I could describe this motion with a graph. So I put my x-axis horizontal, y-axis vertical. I divide my thing into 10 parts. And then let me just plot these points. So I'm moving from left to right in time, and I move up in space. Okay, so and I plot these points. I start at, let me put some numbers here, 0, 5, and 10, roughly. Okay, so then I am at, I need more, so this is 10. Miles vertical and minutes horizontal. Okay, so this is where I start. That's not a good, like this. That's the very first location of ours. And then I do it as well as many times as necessary for each of the time locations. So there is no motion, which means that I will not be progressing vertically. I am progressing only, the time still goes on, but there is nothing happens to our location, so I'm still in the same place. So these are the 3 first locations. So I'm moving from left to right because time goes by, but I'm not progressing vertically because I'm not moving in space. Okay, so and then I start moving finally, and so 3, 2, the next point will be over here. Okay. So, I mean, you can mark it. I didn't mark it just now, but I'll do it with Excel next. So that will be slightly better. This is 2. This is 1, and this is 2. And then I keep going. The next point is here, and the next point is there. 5, 4 here. Okay. And then I stay there, and I could put it like this. So 5. This is just 6 points like this. 6. I think this is right. So once again, this is called the graph. Okay. So the graph is a visualization of the function. The function is the table, and then you can visualize, and hopefully it is better. I don't think I put this 5 in the right spot. So this is 5. Okay, so hopefully it gives you a better view of what's going on, so that you can, in one look, you can tell what has happened here, rather than looking at the numbers that may or may not be have something visible for you to reveal anything. And here you can see horizontal sequence of points suggests that you are not moving, while at the same time, if they're moving, if there is a vertical progress, that means you are moving. You are moving. Okay, and that also it points out in what it points out the direction you're moving in. So hypothetically, if so that's the graph is finished. What if at the last moment at the last minute I was moving in the backward direction? So how about I eliminate this one? Oops, eliminate this one. And where do I put the dot if I start moving backwards?
At 4.
At 4, possibly at 4. In fact, I could put it anywhere I want, or it depends on how fast I'm moving, right? So how about I put it at 2, just to make that point, right? So we actually, during that minute, I was driving so much faster that I skipped the one of the milestones. So I saw the next milestone after a minute, and it was the milestone 2. Okay, so so in other words, I would have here 2 instead of 5. Okay, so let's do the same a little bit. So you can have many examples of this kind. You can do it with Excel. Because it will plot for you automatically. So I have X and Y, and here I have 0. And let me just plot the same thing as we just did. So it was what 1, 1, 1, 1, 1, 1, 1, 1, and then it was 2, 3, 4, and then it was 5, 5, and finally it was say 2. Okay. So that's the same data. I'm just going to plot it now with Excel, which makes it way faster. So I'm plotting the graph. Okay. So the same graph. Naturally, there is nothing else that can happen. Okay. So so you can certainly notice the difference of behaviors of the when you're moving forward and then you're moving backwards. So the fact that you're moving backwards faster, where do you see that fact? If you can, or maybe not here, let me go back for a minute. So where is that fact what makes it that fact visible, that you're moving forward slower than backwards. Do you see it in the graph? Let me try to connect these points so that we can maybe be more specific. Well, like this. Oops, right? And then like this. See, this is the key, right? So you see how the inclined line looks different. The original one, the one on the left, the one on the right. What's the difference?
The difference when you're still moving forward in time, just not in space.
No, you're moving in space, just backwards. But look at what I mean is that the steepness of that line, right? So the steepness of the line on the left is actually 45 degrees. You progress one and one at a time.
So when you decrease or increase speed away, it's steeper, that means you're going
Faster.
faster.
Yeah, that's right. So the steeper it is, the faster you're going. The flatter it is, the slower you're going.
And so that would work with speeding up and going forwards as well.
Right,
Just
well,
shoot up.
right, that's right. So, for example, you can have something like this. It is possible you speed it up, and then you just you skip many milestones. Okay, so it's certainly totally possible. So the slopes is what it's about. We'll talk about that later. At this point, we're still talking about functions. So I would like to do a bit more of this. Okay, so let me just give you a bunch of examples of what can happen, and we'll be entering numbers just by hand, and you see how the graph is changing. Okay, so I will be describing the graph in a way that is hopefully clear. So what if we're going? So let me do what I already did. 0. Okay, so that's the very first example, right? So we covered 1 mile per minute. Okay, what if now let's go 2 miles per minute. Okay, so I'll be just putting here 2, 4, 6, 8, 10, 12, and 14, 16, oops, and 18 and 20. Okay, naturally, unfortunately, the Excel doesn't understand the difference, right? It drew you almost exactly the same graph. Why? Because it does not understand the scale, and so it just shrunk it vertically so that it appears to be exactly the same graph. But as you can see, the x-axis, the y-axis has changed. So it used to go to 10, and now it goes to 20. Okay, so we have to watch out for that. Now here's a trickier question. What happens is with the same setup, but suppose we're moving half a mile per minute. Okay, so we're starting at 0, so it is 0. But we only pay attention to milestones. There is nothing else that we can pay attention to. So what's the second location? There is no milestone there.
So your milestone would still be like.
It will still be 0. Yeah. So you take the record of what? The only thing that you can take a record of is the last milestone you saw. Okay, so the last milestone you saw after a minute is still 0. Okay, and then but after 2 minutes you reach the 1 mile milestone. Okay, and then but 1/2 minute, another minute has passed, you are still there, and so on. Okay, so that would be still a function, as you can see. So here, so you're going to have 5 over here. Okay, so that could be your function. It describes your motion pretty well, I mean, this is certainly uncomfortable idea that you are not, it might appear to an observer, or rather a reader of this data, they might think that you actually did not move at all during that period of time. But it is still there. You can even recognize that the slope has decreased, right? You can see how the general direction of our dots is not like a 45 degrees. It is kind of a slope down, because we went from the horizontally we covered 10, and vertically we covered 5. Okay, so that indicates that the slope has decreased from 1 to 1/2. Okay, how do we deal with this problem in a better way? Well, well. So how do we actually resolve this issue in order to avoid this awkwardness of giving the appearance of not moving? What do? We add more milestones, or well, somebody added more milestones. So we'll, mathematically, what does it mean? So add more milestones, which possibly half a mile at a time. So what does it mean mathematically? More points, yes. More points, and look at the function. Our function, which is description of our function, which is right here. If we add milestones, more milestones, what happens to y? The codomain increases. Nothing happens to the domain, right? So far, at least, we don't have to worry about it. But the domain has changed and has to have more elements. So we change. So change, add more milestones means add increase the size, if you like, of the codomain. So it will be 0, 0.5, 1, 1.5, 2, 2.5, and so there will be 21 of them up to 10 again. Okay, or maybe more if necessary. We certainly expand it. In that case, if I am allowed to have half-mile distances, then I could just go straight ahead and do as I did. I put here 0.5, right? Here 1.5, 2.5, 3.5, and 4.5. So if we were moving without ever stopping, then this indeed is the fair description on the left, fair data describing what is happening more precisely that we have, and the visualization is very straightforward. Let me point out to some extra things that might not be visible right away. So this is the graph. Let me make it clear that this is the graph of the function. But there is another way, another thing for us to see here. So it's seemingly the same graph, but what if I shrink it? Okay, what happened here? Like this. Now let me change. I'm not sure if it is making a point clear. Okay, so ignore the width. Ignore the width. And what are we looking at? I have removed the x-axis. I removed the time out of consideration. Then what's left? Just the location. So this is the road. This is where we were in equal interval of time on the road. So the road is vertical. Okay, so the word for it is path. Okay, so this is the path that we have taken, and it's like taking a shot. What does it look like? It's taking a shot, multiple shots on the same image. Okay, so every minute you take a shot. Okay, and then you will have 11 shots. and then you merge them on one picture. Then you see yourself 11 times, kind of overlapping, or not overlapping, but yeah, overlapping, I suppose. So that's, in other words, it is actually, you cannot see time. So the graph on the left gives you both location and time, but the problem is really it's not reality. You do not see time. You live in time, so you don't see it. But this one, if you eliminate the time, you actually see what you see in real life almost, except it's just the whole period of time of 10 minutes is condensed into one picture. And so you see a bunch of your locations over this period of time. It is not very revealing when the such a motion is so simple. Let's take a different motion. What if we how about we start slow and then we accelerate? Okay, so I start with 0, suppose 0.5, and then I start slowly to accelerate. 1. Okay. What's next? If I accelerate. So during the first the first and second minutes, I covered half a mile. But then I accelerate. How about I cover the whole mile? Okay. And then the next time I cover 3 miles. So it will be a 5. And then I cover 4 miles. It's 9. Okay. And then, I don't know, 16, 15, 16 miles. That doesn't really matter. So you see the graph in the middle, and you see your path on the left. Right, so you can see how close you were initially from your initial location. The next location is very close. The next still close. But then you can see how the gap increases between your consecutive locations. What that is that indication of acceleration, right? In fact, if you in science they do such a thing is that instead of taking a bunch of pictures consecutively, sometimes they take a picture like a video with a flashing light. You've seen it, right? So that flashing light, which means that you will be jumping from location to location. So that continuity of motion is hidden behind it, and so you'll see something like that, roughly speaking. You see a bunch of locations. Usually it's upside down. In fact, let me try to do that. What happens, how do we do a motion that is going down, a motion of, you take an object and you drop it. You know that it starts slow. Say I start at 10, and the next one may be 9.5, then it is 9, then it is 8, 6, 4, 2, minus 3, something like that. Oops, minus 3, minus 10. Okay, so look at the picture on the right, the path, and that's roughly what you see a dropping, a free-falling object. It will start slowly and then accelerate more and more and more, and both of them are visualizations of what you see on the left. So the data is still on the left. That's our function with just a few locations recorded at a time. We visualize them either one of them are pretty good, except especially when it's about motion. The one in the middle is the most common. It is the graph because it gives you simultaneously time, the time intervals, how far you go with time, and then it separately gives you the location which is on the y-axis. I like the one on the right because it is virtually what you might actually observe if you just set up your experiment appropriately. Okay, so any questions about this? Let me show you some pictures here of just same thing but in quicker speed. So I did it previously so that we can go through a few examples quicker. Okay, so data. Okay, so this is once again the motion of that is uniform in speed. I also plotted the table. Remember how when we studied relations, in addition to the data, we also represented in addition to the sequence of what values, input output, which is what the first two columns are. Input first column, output second column. If we think of it as a relation, we see the table. So inputs are vertical, the red axis, and the outputs are horizontal, green axis. That gives us the table. If we rotate it, we have the graph. That's what's on the right. Okay, you can see the axes are still the same. So pretty much, I rotate counterclockwise, right? 9 degrees counterclockwise, and I have for my table, I have my graph. The difference is only that instead of crosses, you have dots. Okay, so then let's see more examples. This one is what we just talked about. When you only record 1/2 a mile and you're moving slowly, but you don't have enough milestone to detect the difference, detect that where you are in the middle. So you end up with this kind of staircase. Now this is motion in the opposite direction, right? So in the opposite direction. So as you can see, compare this picture, the initial picture, as we are climbing along the y-axis. Y is space. We're climbing along y-axis, and now we're going down. Okay, so that's the opposite direction. This one, I don't know, just a general description: moving forward, stopping, moving backwards. That's a story that you might see. This is accelerated motion. Okay, and this is I added half marks once again, so that staircase is turned into a straight line because we detect half-mile locations, and this is what might happen if you going slower and slower. You might have to divide your interval into smaller and smaller intervals in order to be able to detect such a slow motion. So you would not have to stop and move, stop and move. That's a bad impression because the assumption is that the motion is continuous. So 1/2 the slope changes. Yeah, that's the word. Stroboscopic machine that makes these flashing flashes that appear in equal intervals of time, and then you just take a whole picture of them, and you end up with a path on the right. So once again, uniform motion on the left. That you can see how they are equally spaced. The path is equally spaced, and then you have on the right you have how you see how the distances increase in time with time. Okay. So we are moving to something that is becoming more and more important, and that is numbers. So we switched from functions sets and functions of arbitrary nature, sets of arbitrary nature, and now we are looking at numbers. So numbers are more complicated, obviously. Why? Because they have extra structures. At this time, the only structure that we have used was the order. Okay, we did not do any algebra, did we? We did not add, we did not subtract, multiply, divide, nothing of that has appeared yet, and we'll keep it for a while. That direction. The only thing that matters here is the order. So 1 is less than 2, less than 3, and so on. And that is the only structure that we care about at this time. So if you rearrange the numbers, then it might not reveal anything about your data. Here's an example of data that looks random on the left. Why? It looks random only because the order of the numbers is not, it is out of order. Okay, so once you put the numbers on the left, the input variables on the left, you put them in order, turns out that there is a pattern of behavior, which means that it's adding complexity to this is going to make our life easier, not harder, because the pattern will tell us more about what's going on. Okay, so we'll resume this next time.